Good day everyone and welcome to the Breda University of Applied Sciences Houdini Hive Showcase. We're a group of third-year technical artists part of the school's tech outsourcing team. We develop procedural solutions per request for a game project within our year, and we will share some of the work we've done so far.
Hi, I'm Joshua Rizzo and currently in my third year studying visual arts in game design at Breda University of Applied Sciences. I got introduced to Houdini in my first year and since then use it daily for procedural tools and VFX. Currently I'm working on a procedural character pipeline using vertex animation in game engines. Having picked up the newest version of Houdini lately, I'm really excited to work with the new Pyro and Keen Effects toolset. I plan to explore more areas in Houdini like Solaris and PDG to extend my knowledge on industry workflows. The procedural character system is intended to be used for crowds and background characters using vertex animation textures instead of skeletal animations. Basically, this would reduce the performance impact substantially, as this is mainly a shader-based effect and no actual animations and skeletons are used in the engine. Since only one mesh and 2 textures per character animation are exported, it allows to use elaborate deformations with the power of Houdini's toolset. First step is to load the rigged, skinned and animated character. Animations can be added later from the animator to iterate. I then split the rig from the base mesh for further processing. Using the skin weights of the mesh and a custom point controller, I deform the character's proportions. Additional body characteristics such as male, female, overweight and skinny get pre-blended before deforming overall proportions. I then use the base mesh and the deformed mesh in a point deform swap to match the initial rig to the new proportions. After that, I use the new Keen FX toolset to transfer the animations to the new character and bone deform the mesh as the topology and skin weights haven't changed. Additionally, I added support for armor and weapons. The main controller allows changing each armor piece's scale and has additional control for morphing the helmet into different hairstyles. The armor also morphs together with the body changes. Same for the weapons, which morph into different setups. The consistent topology allows to work with one base mesh for all the characters. Finally, the armor and weapon receive the animation from the body with another point deformer. To be able to quickly come back to character setups, an example, if the animation needs to change or new animation needs to get added, I implemented saving and loading presets from text files. Vertex animation is a shader and texture-based solution for animation opposed to skeletal animation. In vertex animation textures, each pixel stores RGB values, which represent XYZ transform coordinates. Then, for vertex animation, the second UV channel stores all the vertices ordered by their number, matching to the top row of your UV layout. In the shader, the values get sampled, transforms get applied, and then the UV scrolls down to the next frame of the animation. The problem is that each animation requires a new static mesh to be exported. To work around that, I introduced a third UV channel and a deformation texture that transforms the mesh before the animation. After this step, the vertex animation can be applied. These two maps essentially define a character and are linked together. To recap, in Engine, a character is basically the same base mesh combined with a tweakable material instance supplied by 2 textures. Previously, the shader required more parameters to be tweaked for each new character. Now, with a custom solution, this comes down to these 3 settings. The deformation map, deforming the character to the new proportions, setting the frame range of your animation, and finally inserting the vertex animation texture. To showcase the variety of characters and potential crowd behavior, I created blueprints in Unreal which spawn units and emulate unit movement for both army and civilian types. This prototype helped visualizing how it could look in the game. I want to thank Side Effects and our university for this big opportunity, and I'm really looking forward to work in the industry.
Hello, my name is Emma Spege and I am a third year visual arts student at Breda University of Applied Sciences. I got introduced to Houdini almost 2 years ago. During my time at school, I became very passionate about creating visual effects, especially in Houdini. My main interests are RPDs, pop and pyro solvers. I'm excited about the new Houdini 18.5 pyro updates, as well as some of the new subnodes. I also want to start experimenting more with the connection between Houdini and Niagara in Unreal. In the future, I hope to be using Houdini at a professional level, creating various effects for either real-time or pre-rendered products. Currently, I'm working on a destruction tool aimed for a strategy game project in my year. In this tool, I focus on texture-based factoring and art-directable destruction simulations, to then be used as vertex shaders in the engine. During this presentation, I will go through my workflow and how I created the destruction for these buildings. Before the model gets imported into Houdini, it needs to meet the following requirements. The model needs to be built from modular pieces, contain 2 UV maps, one for normal texturing and a secondary one that groups the pieces based on the material type, and for the texture factoring, the system needs to have a masked version of that texture that represents the pattern. The first action in Houdini is to separate the model based on its material type. To factor the pattern-based materials, I first scatter points on each modular piece with the mask applied, then I delete the white points and use the remaining points to create a wire. I extrude this wire and cut through the walls using booleans. For the root, firstly I reset each beam to the world origin and rotate them based along their longest axis. Then I scale each piece down in its length and apply a Voronoi fracture. Afterwards, I scale the pieces back up and place the pieces back to its original position. Before I set up any constraints, I first isolate and simulate the small pieces of the building. Afterwards, I select start positions from where the constraints should start dissolving. Then I select some areas that will be reserved to create leftover ruins. The dissolving rate of the constraints is controlled by a curve. This curve controls the overall flow of the destruction. After simulating and caching, I use the Labs Vertex Animation Texture ROP to export the FBX, the vertex animation textures, and the original UVs that came with the imported model. To apply the different materials in Unreal, I set up a material function that uses the ID UVs to create a mask for each material. Then the materials are applied back to the normal texture UVs. This way I do not have to apply multiple materials for the same building. In Unreal, I use the pre-made vertex animation shader setup to apply the vertex animations. To apply different simulations to the same building, I only need to change the material instance and apply the new vertex animation textures. I created some additional parameters to the shader that controls the time and start of the simulation. Because the entire simulation is controlled by material parameters, a blueprint can easily be set up that changes these parameters to interact with the building. To close off this presentation, I want to thank SideFX and BUas for this amazing opportunity, and I can't wait what the future holds.
Hey everyone, I'm Jens van Kamp and I'm a third year game art student. I focus on both technical and environment arts, my favorite being nature-heavy landscapes. I seek expertise in combining these two to create gorgeous simulated worlds and help in making the creation of these intuitive and efficient. All projects combined, I've been working with Houdini for about a year now. I use Houdini primarily for creating game tools, primarily oriented at procedural modeling for environments. For my third year projects, I'm working on Ambition's tool suite to process and populate large-scale landscapes for open world games. I call it WorldGen, and it's a collection of tools like an ecosystem simulator, a river and lake tool, a rock formation simulator, a road network system, and more. I'll probably continue using Houdini for tool creation and procedural modeling primarily, but I'm also interested in flip fluids and simulations as well. I feel like I've only scratched the surface of what this program has to offer.
Let's get right into what I'm going to be showing you today. This presentation will be a quick first glance at my WorldGen tool suite, which I'm currently developing for an open world game project at our university. Needlessly to say, the assets used are placeholders and the tools are still in a primordial state, but the base stands and gives a good idea of what's going to be possible from the client. To showcase the tool suite in action, I created an example scene in Unreal from satellite data. These mountains are an 8x8 kilometer section of the Swiss Alps and are scaled to real life. WorldGen is built for handling large terrains like this and works together with level streaming solutions. This makes processing landscapes modular, fast and iterative. Artists and level designers have powerful control over ecosystems, river placement and more, while taking over the natural development logic and manual labor. Let's get a closer look at the system, starting off with the texturing of the landscape. This is the starting point of processing terrain and uses minimal input. The system automatically creates landscape layers based on things like ecosystem type, water geometry, slope angle and terrain elevation. It's possible to either generate from scratch or paint custom information on top and preserve it as much as possible when you're rerunning it. The way you decide a set of processing rules per individual area is through ecosystem painting. This can be done in the engine, and ecosystem rules can be intuitively created in Houdini by artists. These ecosystem recipes drive not only texturing, but foliage growth as well. Foliage growth is simulated using terrain attributes, and artists can set favorable living conditions for individual species. Using so-called species scatter digital assets, users can easily compose complex systems by masking favored living conditions for that species. This way, terrain attributes can be translated into places and species would thrive, and these specimens are then assigned a viability value. Species will rival each other inside the competition radius based on this value. The better the living conditions are for a species, the more likely it is to drown out others. This way it's possible to simulate realistically distributed foliage species. All of these species together are combined into the large entity point cloud that gets exported to the engine, where the final assets are being placed on top of those points. Moving on to the creation of water bodies and rivers. The way you can create lakes is simply by using a water plane like you normally would. Both the landscape texturing and rivers will then interact with these planes. River curves can be created in engine and will automatically impact the terrain to fit it. Rivers automatically meander and cascade based on the terrain, making them look very embedded into the landscape. Rivers can also never move upwards and will create canyons instead. After creating the geometry and adapting the terrain, the river is then further processed by adding things like vertex color based on slope. This information is then used in the water material to make it stream faster near cascades, as well as adding particle systems in those areas. Because the other tools are still in the midst of development or in queue, this is all I've got to show for today. I would like to thank everyone watching for the time and interest, and especially thank Side Effects and the iGet program for the opportunity to showcase my work. Now let's quickly move on to the next presenter in line.
Hi, I'm Alex, a third-year student here at Breda University. I'm a technical artist focused on anything procedural, but I have a special interest for terrain generation. I've been working with Houdini for a little over a year now, with my first ever creation being a building generator. Since then, I've loved the process of creative problem solving that goes into working with Procedural. I use Houdini to create tools for environment artists and level designers to populate worlds. I'm particularly interested in the intersection between environment art and procedural. I'm currently working on a landscape creation tool for a large open world survival game set in the Atacama Desert. It'll be my first time exploring terrain generation, which I'm excited about. I would have to say I'm most excited for the official release of Houdini Engine version 2. I'm curious to see how much more we'll be capable of doing in-engine. Ultimately, I aspire to work on large, open-world projects where procedural can be used to populate large, luscious worlds.
Hi, my name is Peter Prickards and I'm a third-year tech art student at Breda University. I started using Houdini in the first year of university and it's by far the program I use most. I'm using Houdini mostly for environment art related procedural modeling and automating pipelines. Currently, I'm working on a custom pathfinding solution to generate road networks. I'm really looking forward to Houdini Engine v2 for Unreal and the Python 3 implementation in Houdini. We are going to talk about a track generation toolset for a racing game in Unreal Engine 4. Here you can see some gameplay footage of the game. The track has a non-linear design to allow the player to choose their own way by going in a different direction on intersections or splits. There's also portals that allow you to go to a different dimension to either avoid or find other players. We had quite a few requirements for the toolset. It needed to be very user-friendly, as level designers aren't necessarily familiar with using Houdini. Also, we needed a lot of customizability as the track directly affects gameplay, and we needed fast iterations to get quick gameplay prototypes working. Our choice there was to go with an interface in Houdini directly and to utilize Python viewer states to allow designers to interact with the interface. Here you can see one of the viewer states in action. It allows the user to change the size of intersections, the scale of the road, and also the banking. What happens under the hood is the viewer state changes the parameters on this HDA, and the HDA then actually changes the road mesh. Here's another example where the user can just draw on the track to create a fence and also remove it. Users requested to be able to make small changes in Engine as well. We utilized Houdini Engine to do this and then allowed the user to export these changes to a JSON file. The JSON file can then be read back into Houdini, which makes this workflow very non-destructive. This is a sped up video of the track creation process from start to finish. Here, shelf tools are used to navigate the network and edit these curve nodes. Then, the viewer state shown before is used to change intersections and banking of the track. Now in Unreal, small changes to the track are made and saved to a JSON file. This is then loaded back into Houdini, where the user proceeds with adding fences. This is again saved in the JSON file and loaded back into Unreal. As a final step, bounding boxes are used as input for placing procedural caves and arches.
On the visual side of the tool, the detailing system I created takes the basic track geometry that Peter's toolset creates and replaces it with appealing visuals. So how does it work? Instead of the default sweep, the system segments the track geometry by the 4 module size categories. The modules are generated from these primitives, much like through a creep node, except done in Vex. Let's dive into how it works a little more. It all starts with a track profile which is sectioned and ID'd in preparation for the modules. The system is set up in a way that it can accept any profile, including closed tunnels. Next, the section profile is swept across the track and processed further to accommodate for the adjustment of the segment length as well as the track width. To deal with this variation, the system creates buffer geometry between the modules. In the final steps, the track is generated, along with the smooth transitions between varying track profiles. Additionally, arches can be added for some extra visual interest. Here are the modules that I created specifically for our game. The benefit of this approach is the ability to easily swap out modular inputs, as well as add variations to each category of module, should the user wish to. And here you have the final result.
And with that, we've come to the end of our Houdini Hive showcase. We'd like to once again thank Side Effects and our university for the chance to show our work to you today, and we hope you've enjoyed it.